Hi there, this is exercise 7C.1. By point 1 it implies there's more than one. I'm hoping to do this in two. And this one I want to show you how to do some integrations, and in the next one I want to almost show you why those integrations work. But certainly this one's the mechanics of doing it, making sure we get the answers. And those answers tend to always be inverse trig or inverse hyperbolic functions. And this, if you remember, is one of those. I think this is the inverse sine. But let's go back a step before we do that. There, I've got some differentiations that we've been playing around with recently. These are the differentials of inverse trig, and these, of course, are the differentials of the inverse hyperbolic functions. And they're very similar, and that's why they're in the formula book, because without them, you can't be expected to remember. Well, perhaps you can be expected, but then they don't expect you to remember every single detail. First of all, then, this is a differentiation. I've got x minus what is effectively a product, so I want to deal with the product first. So let's differentiate this. The x isn't going to cause us a problem. So the x is the square root of 1 minus x squared. That's the u, sorry. And my v is the other function, the inverse sine of x. And you should remember the rule. It's uv dash plus vu dash when you differentiate something times by something else. And of course it is something times something else because it's there. There's a little times there, honest. So if I differentiate this, well, it becomes, well, this is really 1 minus x squared to the half. So the half comes out to the front. And it's the 1 minus x squared to the minus a half. We lose a power. But then I'll have to times by the differential of that, which is times by minus 2x. What's that give me? Well, the 2 times by half disappears. It's minus x. I'm half tempted to rewrite this 1 over the square root of 1 minus x squared, because that's obviously to the power of half is a square root, and it's a minus, so it's on the bottom. And v dash, what's v dash? V dash is, well, it's inverse sine, so I've got it here. It's 1 over the square root of 1 minus x squared, which is obviously similarities there. So if I come back over here, dy by dx, not sure if I've got any room here, because that'll be an answer here somewhere. Dy by dx is, well, if I differentiate the x, I get 1 minus something. So I'm going to put that in a bracket because it's more than one thing going on here. It's, as I said up here, it's uv dash, so it's the square root of 1 minus x squared by v dash. Oh, right, that is 1 over the square root of 1 minus x squared plus vu dash, or v is the inverse sine of x times by this little lot. Right, it's probably best written minus x square root 1 minus x squared, close bracket. And the great thing about that is that cancels with that. So what's this give me? That could be 1 minus bracket 1, minus the x. I'm going to write that first, x over the square root of 1 minus x squared times by inverse sine of x. And 1 take away 1 disappears, and the minus and minus becomes a plus, so I think the answer is just simply x over the square root of 1 minus x squared times by the inverse sine of x. So that's a differentiation, which is right, which is more or less the same as we've seen before, perhaps a more complicated version of it, but we've seen these differentiations before. So now I want to look at the opposite of those. So for instance, we just go back a step. We've said the inverse sine, if you differentiate, is 1 over 1 minus x squared. So don't be surprised. Well, interestingly, these are very similar, but the more general versions I give you here. But 1 over 1 minus x squared would be the inverse sine of x. It's the opposite way around. If I integrate that, I get this. And in fact, we extend it slightly and say what happens if you get different numbers here, because quite very often we do. You'll notice there's an inverse sine, but there isn't an inverse cos. And these are the ones they give you in your formula book in the exam. So inverse cos doesn't appear, and there's an inverse sine, or there's an inverse tan, that's okay. But there's an inverse sine, there's an inverse cos, but there isn't an inverse tan. That's not in the formula book either. And these two missing integrations that are missing, well, you could write them, and I went and dug them out because I thought it'd be interesting. This one is missing because you'll notice it's almost identical to the inverse sine. This one says 1 over. So it ends up, this is right, and you could write it, but you could just call it a minus inverse sine instead, because of that minus at the top is their own difference really. So in reality, you don't need it, so I wouldn't worry about that one. This one, I have seen in formula books in the past, and you might want to learn this one, or you might not, because you can actually do it using partial fractions, and we'll come on to that perhaps in due course. So just be aware of that. These are meant to be used, but don't have to learn them off by heart. Now I'm going to show you a method now. As I said, I'm going to teach the mechanics of doing this, but it's not necessarily going to identify why this works. So I'm going to try to do that next time. If I was given this to do, my initial thoughts are, well, the 4, none of these are 4s at the top, so I'm going to move the 4 there and just pretend it's a 1. And I'll just effectively times my answer by 4. But then I'll look at it and I think, which one is it? Is it it's a square root of 16. I think it's the inverse sine again. It's this one. It's a square root, and I've got a number minus x, a number of x squared. So the temptation is to say it's inverse sine. And you kind of, it says a squared, so I'm thinking to myself, well, the a squared is 16. Or put a different way, a is 4. And it says x squared over there, so kind of my x squared is really 25x squared, or put a different way, my x is, I'm going to put arrows, but I think I prefer that, is really 5x. And so I keep on saying this word temptation because it implies it's wrong. The temptation is to say to yourself, well, now I know what my a and my x are, I can substitute that into my formula, and it's going to end up being 4, because I had a 4 at the front, inverse sine of x over a. Well, my x was 5x, and my a was 4, and so that theoretically should be my answer, and it should be, but it's not. And there's a trick here, and what we need to do is divide by the 5 from here, and the number of x you have to divide by it. And I'll want to show you why that works in due course, but for now, really, I just want us to know the answer, and the answer is 4/5 inverse sine of, yes, that works. So notice that trick, this divide by the number of x. And it comes back to being almost like an inverse chain rule question. The number of x in our x substitution, effectively. So just bear that in mind. Let's look at another question. This says 3 over 9x squared plus 5. So I'm just looking at this. I think it's this one. This is the one which hasn't got a square root, and we haven't got a square root, so it must be that. So what are we identifying? Well, for the start, the number a squared is the 5, so therefore a must be root 5. And we're saying that the x squared is really 9x squared, so I suppose we're saying that the x is really 3x. So when I substitute this in, I'm also not allowed to have a 3 there, I'm going to have a 1 there with a 3. So I think my answer is 3 times by, and it says 1 over a, 1 over the a, inverse tan of x over a. What was my x? My x was 3x over root 5 plus a constant. So it's a bit of a mess, but remember, this is not right. There's a trick, and it was that divide trick. The rule said divide by the number of x you've got, which is 3. So I'm going to divide by 3. Oh, that disappears. So I actually reckon that's my answer. My answer says 1 over root 5 inverse tan. Yeah, so that's right. So remember that trick. We do get some harder ones which will need a bit more work. And the reason is because we've got so many x, and this at the moment doesn't look like, well, it hasn't got a square root, so it must be this one that I'm trying to get it equal to. But at the moment it's got this middle 4x thing, so I can't do it. So I'm going to complete the square. And when I complete the square, I'm hoping that this then works. So let's have a go. What have I got to do? Well, I think I've got to x minus 2 squared I take away the square, add the 13, so I've got x minus 2 all squared plus 9. And of course it's 1 over that. Now if I write this as u equal to x minus 2, and this is what I want you to think about, that gives me the integral of 1 over u squared plus 9. And suddenly, I need to just think about the dx. du equals, well, du by dx is 1, so therefore du equals dx. I can just write du, which is suddenly a very, very similar thing to this. And you'll notice I've not got a complicated x, just my u equals x. I don't have to worry about anything there. The only thing I've got is that a squared is 9, so therefore a is 3. And so I'm kind of thinking to myself, the answer here should be 1 over the a, the inverse tan of, well, it says x, but of course I know that's u over a, 3. That's a constant. And I suppose I then have to just change it back into x's. It says u, and u is x minus 2, so I get this. And that's right. This is what we've got to do. Notice I didn't, on this occasion, have to divide by the u, any number at the start, because u equals x or x equals u. It didn't say 5u or something. This one's slightly different again. So this is now the integral of, well, let's get rid of that first of all. I don't like it. It's a square root one. And it looks to me to be that one. It's got a minus in it, but it's got this funny thing first. So let's see if what I can do with this. I'm going to write minus x squared minus 6x plus 7. I'm going to take out the minus, and then I'm going to complete the square. So it's minus x plus 3. Better put this in a bracket. Squared minus 9 plus 7. And then if I get rid of the bracket, I can write it, that's plus 9, because it's minus and minus, plus 7 plus 16. So I reckon really I've got 1 over the square root of 16 minus u squared, if I set u equal to the x plus 3. And again, du by dx must be equal to 1. So this says du. And this, as I said, looks like that, so I think this is the inverse sine of x, which was u, over a, and a, well, a is 4, and plus a constant, and if I just, rather than write the x, I can write x plus 3 from there, and that's the answer. Now I've got one last question. Now this is a bit of a trick one. So I've kind of pointed out already that I could complete the square, but a better trick is to spot, you can write 2x minus 3 all squared. So if I now write u equals the 2x minus 3, and check that if you don't believe it, that gives you this if you multiply it out. And it's a bit of a trick, but now I've got that, I can write this integral as 1 over, well, it's a square root of u squared, what's this, minus 16 here. Now, du by dx this time is 2, so presumably I'm going to have to write 2, I'm sorry, du over 2 when I switch those around. So, which one does that look like? It looks very much like this one, I think. So this sounds to me as if it's a half the inverse cosh of u over the 4, because it's the square root of that plus a constant. Now if I just change the u, what was it? U was 2x minus 3. Let's see if that's right. A half the inverse cosh of 2x minus 3 over 4, because a constant is right. So at this stage, all I've done really with you is done a bunch of questions which lead, and I've taught you the trick. And I suppose that the area where you're going to most likely fall foul is that divide by trick. So go back over that, make sure you understand why you're dividing, not so much why, but when you're going to divide. do some questions. I'm suggesting questions 1 to 3, first column only, unless you get keen, and then next lesson we'll see why this works. Good luck.